Hello everybody, welcome to this MathWorks webinar. My name is Javier Gazzari and I am an application engineer with the MathWorks. The topic of today's webinar is real-time battery pack simulation and multi-core targets. And even though the example that I will show you pertains to battery technology, the functionality that I will describe is pretty much applicable to any dynamic system whose real-time simulation performance we wish to improve by partitioning the model for multi-core execution. During the past several years, we at the MathWorks have been devoting quite a bit of effort in developing battery cell models that contain an equivalent circuit inside whose elements have a parameterization that is a reflection of the electrochemical fingerprint of a battery under consideration. And stacking together blocks like this one here, we can design battery packs like the one that you are seeing an example of. In this case, an 8 cells in series battery pack. So this is very good for desktop simulation. Now in this project, we wanted to go a step forward and do real-time simulation. Real-time simulation is a very useful technique that involves the interaction of some hardware with a model of the plant to be controlled that runs in real time on a real-time computer like the one that you are seeing in the background. As you can imagine, this is a very complex setting, and it involves a substantial investment. Once a company does such a kind of investment, this system becomes in very high demand. So we believe it would be very, very useful to count on a couple of techniques in order to ensure that the model is real-time capable and its performance is as good as possible. So here are two ideas in order to prepare your model for real-time simulation even before you get to the real-time system. The first one is to create and configure and actually automate creation, configuration, and modification of the Simulink model that you want to run in real time using MATLAB scripts. And we will see how this is done. And secondly, to profile that model in such a way that we have at least a qualitative indication of how well the model is going to perform on a multi-core target when it runs in real time. So let's say we want to run this 8 battery cell model in real time in a computer, a real-time computer like the one that we are seeing on the screen. The more sophisticated, the larger the model is, the more difficult it becomes to make it real-time capable. Now, manufacturers of real-time computers offer us multi-core capability, that is to say a processor with multiple cores, in order to make this real-time capability easier to achieve by offering us the possibility to distribute the computational load of the model onto the different cores. So for example, I could think of partitioning my battery pack model in 4 equal parts where each part contains only 2 cells of the 8 cell series connection. Now, it is also true that by partitioning the model, we have unavoidable potential problems such as latencies, that is to say, delays in communication between different tasks, and that may affect adversely the execution of the model or the integration of its differential equations. In addition to that, there is an overhead imposed by the scheduler that needs to do the partitioning that also needs to be taken into consideration. In addition to that, there are in general many possibilities when it comes to choosing the right partition. For our example under consideration, we can also think of partitioning just in two parts with 4 cells each. So there are many configuration options, and it is not clear from the beginning which one is best. So it would make a lot of sense to have a technique to help us decide in as quickly a manner as possible. So the question is, which one is better? For example, an 8-cell battery pack partitioned in 4 parts or just in 2 parts? For this, we will present a couple of techniques. One of them is desktop profiling, which is going to give me a qualitative indication of the implications of partitioning them all even before going to real time. And secondly, I will show how MATLAB can script and therefore help us automate model creation and configuration so that we can try out different types or architectures when it comes to partitioning and choose the best. When you want to partition a Simulink model for parallel computing, you can use a functionality called concurrent execution. Using concurrent execution involves dividing your Simulink model into different tasks using a certain criterion. For example, sampling rate. Then the scheduler of the operating system is going to assign those different tasks to the different parts of the computer cores. So let's see the options that we have for this particular example. When we have 8 cells connected in series, we can think, for example, of just one task partition where all the cells are assigned to just one task and in which I can expect minimal concurrency. I can also partition the model in 2 tasks with 4 cells each, or in 4 tasks with 2 cells each. Let's switch now to MATLAB and see how we can create models and modify their architecture to improve their real-time capability. So what I have here is a MATLAB script that contains the information for the model architecture and its configuration. This is going to be the name of the model, battery 1, because I am going to ask for one partition with the 8 cells on it. This indicates that the execution rate is going to be 1 millisecond. And I have 2 options in terms of whether I want to configure the model for desktop simulation or real-time simulation. So what these functions are going to be calling are the methods in this class called battery model. And I want to bring to your attention 2 types of MATLAB functions that are very useful in this case. Let me maximize this for better view. AddBlock creates or puts a predefined block into a Simulink model, and AddLine connects Simulink blocks to each other. So let's execute this model and see what MATLAB can do to create a model in Simulink. So what do we have here now? The battery stack is here. If I double click it, I should see the 8 cells connected in series. These are input, so in this case, temperature, 20 degrees centigrade is constant, and the type of load. So the different options for discharging the battery stack. So in this case, I have pulses, constant current, and a drive cycle. And here I have a scope to monitor what's happening. So I can execute this for a few seconds. First compiles, and then it starts running. In this case, it's running a drive cycle. So what we need in order to do all of this is to have ready for us some predefined blocks. So in this case, these are the different blocks that will constitute the model references, and the MATLAB script will be in charge of connecting them together. Let's stop it for now and create another one. Let's close this out. So let's now suppose that we want to create the other version. So 2 stacks with 4 cells each, right? Same physics. Let's call it 2 here. Same physics, but different configuration for real-time execution. So what I have here is 2 model references with the 4 cells inside. The last option will be with a 4 here, 4 and 2. When I execute it, I see my model with 4 model references, each of which has 2 cells connected in series. So instead of running this model, let's do something different. So I had told you that these color rectangles define the task assigning, right? So if I click on them, I have all the list of the partitions with its 1 millisecond period. But one important thing that I wanted to show here is the profiling. So what this is an analysis of how the computational load is going to be distributed in for the 4 tasks. So we can see that in this case, the computational load is fairly evenly distributed. And this is, as we will see later when we compare it with real-time results, is a good qualitative indication of what will happen in actual real time. So let's close this out and go back to the presentation. A few minutes ago, we were referring to latencies or communication delays that were an unavoidable consequence of partitioning. And we have to make sure before we do any attempt at improving the real-time capability of our model that these delays or latencies do not negatively affect the capability of Simulink to solve the differential equations necessary for simulation. In order to check that, what we have to do is validate our model or each partitioning option of the model. So what we are proposing is to compare the simulation results of each of the three options for partitioning, namely 1, 2, and 4 partitioning schemes, against a benchmark which has no partition, and it is also executed using a variable step solver to give us the most flexibility. These were the results that we obtained. This is a simulation of a pulse discharge where we are observing the voltage of the 8-cell battery stack as a function of time. And as we can see, even though it's not absolutely perfect, the matching is sufficient for us to be able to say, okay, these proposed three partitions are okay in the sense that they don't introduce any undesired artifacts. So let's see now what the result was for the three partitioning options in terms of the desktop level profiling. When I did this in my laptop with these specifications, I found that it took 209 microseconds on average for the one task partition to execute the battery model, and almost negligible amount of time for the rest of the blocks. The battery stack is, of course, in this case, the part of the model that takes the large majority of the computational burden. What happens with a two-task partition? Well, more or less the computational load is evenly distributed between the two tasks, and something similar happens when we compare the four-task partition. Now, keeping in mind that we're doing all of this in order to hopefully get better results in real-time execution, the question is, well, how or to what extent are these desktop level results indicative of something that will be observed in real time? So here, what we're doing is comparing the profiling results for the desktop and the real-time simulation done in a computer whose specifications we can see in here, running Simulink real-time, which is the real-time kernel offered by the MathWorks. And in this case, this is the one task partition. So we can see here in the y-axis that these are the tasks. By far, battery stack 1, which is the only task assigned to battery cells or battery cell blocks, is the one that has the most computational time, which is expected. The small number at the bottom left corner of each of the bars indicates the core identification or number in the real-time computer. So, for example, we can see that there is concurrency, right? There is overlap between the or among the different cores, but also it is the case that, for example, let's say core 2 is first used by add voltage, this task here, and cannot be used again until add voltage is done with it. The second time that core 2 is used is by load. So in this case, we obtain about 60 microseconds of execution time, which is not the same as the 209 that we had obtained before. And one of the reasons why is that, well, we are talking about two different computers, two different pieces of hardware. So quantitative matching is not to be expected. How does that compare when we are observing the two-task partition option? We can see that, again, there's evident concurrency here, And now the two tasks that are in charge of executing the battery stack show 30 and 35 microseconds. The 4-task partitioning option shows task execution times between 20 and 23. Again, not qualitatively the same as the desktop prediction, but we can see that the computational load is more or less evenly distributed as it had been predicted by the desktop profiling. And finally, this table summarizes the comparison between the desktop and real-time results. What we are seeing is in rows the 3 partitioning options, and in columns the desktop and real-time options. So if we compare 1 and 2 task partition, what we observed is that it took 50% of the time to execute the 2-task partition with respect to the 1 task for the desktop, and about 54 for the real time. Whereas if we compare the 4-task partition against the 1-task partition, it took an average 28% of the time to execute the 4-task partition, whereas 36 was the number when we are comparing the real-time results. So again, not exactly or quantitatively accurate, but a decent qualitative indication of what to expect in real-time execution. Let's now summarize the key takeaways from this webinar. The objective was to prepare a model for real-time execution, but before we have access to the real-time system. That is to say, what can we do before we have access to the real-time system at the desktop level to ensure that the real-time execution performance is going to be as good as possible? 2 ideas we brought to the table. One of them was to create, modify, and configure Simulink models using MATLAB scripts. We saw that it was relatively simple to automatically construct different architectures of Simulink models for the same physical system using MATLAB. And secondly, we used a tool in Simulink called profiling, a feature of the concurrent execution functionality that allowed us to observe the distribution of the computational load for a partitioned model, and that gave good qualitative information about what is to be expected for real-time simulation. For more information about the procedure and the results of the project that I just described, please visit our website. There's an SAE paper published with all this content at mathworks.com. With that, I would like to conclude this webinar. Thank you very much again.